Hi, everybody. My name is Levy, and my group includes Elior Nehemya, Tal Ben Senior, and Daniel Benatar. And today we're going to present you VoltJockey, which is an attack that aims to breach TrustZone by software-controlled voltage manipulation over multi-core frequencies. So first we're going to start with what exactly is TrustZone. So in general, we have a lot of sensitive operations that we need to execute, for example, encryption methods. To do that, we need the CPU to have a trusted execution environment that isolates these operations and maintains their confidentiality, integrity, and availability. CIA triangle. So this is essentially a trusted execution environment, TEE, and an implementation of that is the TrustZone technology, which is developed by ARM and is an extension for ARM processors that exist in a wide array of devices, for example, the Google Nexus 6. So this TrustZone has been proven useful defending against various software-based attacks, which were easily patched by software upgrades. But what it did is it also forced attackers to be more creative and look for other attack vectors, for example, side channel attacks and hardware fault injections. Previous work by Tang et al. Introduced the clock screw attack, which broke TrustZone by overclocking CPU with software. But it was easily patched. It was easy to address this vulnerability because you can always lock the hardware frequency. The authors of this paper introduced a new attack, which is stealthier than clock screw and is called VoltJockey. It is based on the same hardware fault injection attack, but it uses voltage manipulation instead of manipulating the CPU's frequency. How does VoltJockey exactly inject faults? First, we need to understand something about multi-core processors. Multi-core processors often have the techniques that ensure energy efficiency of the processors. This is called the DVFS, which is then dynamic voltage and frequency scaling. DVFS has an inherent vulnerability that we are going to talk about later on. And VoltJockey exploits this vulnerability in order to perform two experiments that one of them is to obtain the key of the AES encryption, and the other is to invalidate an RSA verification that intends to load a malicious application into TrustZone.
The energy consumption of a device is determined by the integral of its dynamic power consumption over time. In order to reduce the energy consumption, most of the current processors enable the dynamic voltage frequency scaling, DVFS, which dynamically adjusts the frequency and voltage of processor cores based on the real computation load. On one hand, we earn a more efficient energy management tool. On the other hand, the DVFS allows a privileged user to change the frequency and voltage via software interface. Normal activity of the DVFS will follow the vendor stipulated operating performance points, i.e. OPPs, which attach a frequency with a particular voltage that guarantees error freely and energy efficiently. So now we will try to understand what happens when we operate in different voltage frequency points that are not in the operating performance points described by the vendors. To do so, we will look at this toy example circuit. Here we have two flip-flops and the logic unit in the middle. The middle logic unit transfers the output of the first flip-flop to the input of the last flip-flop in a sequential way. Whenever the clock pulse is rising, the flip-flops trigger and store the input signal they get at that exact moment. This update takes a small amount of time, which affected by the voltage. High voltage will cause smaller delays, and low voltage will cause higher delays. In addition, the middle logic unit also delays the propagation of the signal. We'll denote this time as T transfer. In order to get normal operation in our example, T source plus T transfer has to be smaller than T clock minus T setup. If the provided voltage is lower than the expected one, T source and T transfer will increase, which might violate the timing constraint. As we can see, now the output of the last flip-flop is incorrect. Here we get 1 instead of 0. VoltJockey will violate this timing constraint to inject hardware faults into the victim's procedure.
After Elior specified the details of how to trigger hardware faults by voltage manipulation, we will now introduce overview of the VoltJockey attack. First of all, the attack takes advantage of the multi-core processors to induce hardware faults. Two cores are used, one core used as the attacker core, and the second core used as the victim core. Our aim is to provide high frequency to the victim core and low frequency to the attacker core, and give the processor a voltage that is sufficiently high for the attacker core to perform tasks correctly, yet leads to fault in the victim core. That particular trick will allow us to collect error output for differential fault analysis from both cores later. Here is the operation performance points graph Elior explained before, which are the recommended voltage frequency tuple required for the procedure to work correctly. From the graph, we can see that we choose a voltage of roughly 0.93 at a particular frequency in the victim core, which is distant from the area of the recommended points, which leads eventually to hardware fault, yet won't crash the procedure. At the other end, we choose a lower frequency at the same voltage for the attacker core, at a point which performs tasks correctly, and thus help us to perform differential fault analysis. This leads us to the first step of the attack, setting environment, or preparation setup. First, we need to configure the victim core with high frequency, and set the other cores to low frequency. Secondly, we need to find appropriate processor voltage that leads to fault on the victim core and perform tasks correctly at the rest of the cores for suitable differential fault analysis. The second step is, once we found the suitable parameters for the attack, we need to wait for the targeted attack's function to be invoked. The third step, previous delay, includes waiting for the appropriate time between the function executed to the particular instructions of the data we aim to manipulate. The fourth step is actually the attack itself, where the voltage glitch is performed, regarding the parameters we found in the first step. We can see at a figure that the fault happens solely on the victim core. The last step is restoring voltage. The ultimate goal of the attack is to obtain sensitive data or temper the functions of the victim process, other than crashing the victim core. Therefore, attacker procedures need to restore the processor voltage to resume the victim procedure normally as soon as the fault injection is done.
Now, we will talk about two applications of the VoltJockey attack. The first one uses VoltJockey to inject faults into the AES encryption algorithm with the ultimate goal of obtaining the 128-bit key. We know that brute forcing AES key is very hard. However, there have been a few studies on injections of faults into AES that could greatly reduce the space of possible keys. If we inject a byte error in the input of the 8th round of AES, just to remind you, AES includes 10 rounds. So this 1 byte error we injected will propagate to 4 error bytes of the input for the 9th round because of the mixed columns method of AES. Then, At the 10th and final round, the error will be present in all of the 16 bytes. Finally, by analyzing the input of the 8th round and the output of the final round, the attacker only has 2 to the power of 8 keys to search from, according to mathematical hypothesis. The second experiment with VoltJockey aimed at bypassing the RSA verification to load malicious applications into TrustZone. According to previous works, RSA is also susceptible to fault attacks, just like AES. RSA security guarantees are based on the computational complexity of factorizing the public modulus N. The formula for the decryption algorithm is at the bottom, for those of you who don't remember. If we inject faults to this N, we can change it to a slightly different number, which is now easier to factorize by a lot. That way, the decryption algorithm of RSA will malfunction, and we can sign malicious apps as if they were benign.
In this section, we will discuss possible hardware-based and software-based countermeasures to the VoltJockey as well as some future extensions. First, we will talk about hardware-based countermeasures, like limiting voltage. Limiting the core voltage to break the voltage differentials is effective to prevent VoltJockey, but will introduce more energy waste. Abandoning shared hardware regulator. This is achieved by ensuring every core has its own hardware voltage regulator. The shortcoming of this design is that energy optimization is achieved on a local core rather than the entire processor. And lastly, separating the secure core from application cores. The secure cores can be redesigned and are separated from application cores, but the design will be resource waste and enrich the hardware cost. Now we will see software-based countermeasures, like integrity verification for regulator driver. This means that the credentials of the regulator driver can be generated and stored in the secure boot image before releasing the software system. And lastly, the trusted voltage monitor. Trusted processes based on trust zones can be developed to continually monitor the core voltage and frequencies. Now we will see future extensions, like attacking other crypto systems like DES or ECC. Being a general attack helper, VoltJockey can achieve malicious data modifications, which may help attackers prepare vulnerabilities for other attacks. And lastly, attacking SGX. VoltJockey proved to be effective in SGX. The authors have another paper on this matter. And now we will see the summary. VoltJockey was deployed on ARM-based Crate multi-core processor, whose core frequencies can be different, but the processor voltage is controlled with a shared hardware regulator. VoltJockey is a hardware fault-based attack to TrustZone using software-controlled voltage manipulation, which exploits the voltage management vulnerability of DVFS. The attack method can successfully reveal the AES key protected by TrustZone and breach RSA-based TrustZone authentication. ARM TrustZone is a system-wide secure technology that is utilized in billions of devices. VoltJockey proved to be successful in a commercial device and demonstrate to be dangerous in the secure execution environment. Thanks so much for listening, and if you have any kind of questions, please let us know. Bye-bye.